So in our last video, we introduced the idea of continuous growth, specifically in a financial context. But what we're going to talk about now is just the general idea of continuous growth and decay, not limited to financial context, but just to any sort of problem. So a quantity grows or decays continuously if we can be modeled by an exponential function of this form, which is basically the same as the financial model we looked at a moment ago. It's just sort of relabeled. A lot of times you see this as P of t principal times e to the RT. You see that in a lot of sources, and it doesn't have a little c on it, and that can be a little bit confusing for someone who's taken this class, but we're going to use this C notation mainly because we've used R so many times for so many different things that, well, it can be confusing. So, we've got R as the correlation coefficient, R is the growth rate, and now we've got R sub C. Now, what does that mean? So what is R sub C? R sub C is the continuous rate. Continuous rate. Okay, so we've got it right here. Now, this can be positive or negative, and if it's positive, then we've got growth, and if it's negative, then we have decay. So this RC, depending on whether it's positive or negative, represents one or the other type of growth. Okay. Now, one interesting thing about this is that we can actually convert from this continuous form to the standard form, and really all we have to do to make that conversion is down here. So this is the connection between the continuous growth rate and the regular growth rate. So in other words, what we're saying is that if I write a model in continuous form, okay, I can rewrite that same model in non-continuous form, a times b to the t, which is also equal to a times 1 plus r to the t, right? Where r is equal to e to the r sub c minus 1. Now that may sound a little scary at the moment, but I promise this is not really that bad once you get used to it. Okay, let's look at an example where we do something with this. Under certain conditions, Escherichia coli, which is E. coli bacteria, grow at a continuous hourly rate of about 20%. So there's that word, continuous. And this is a continuous hourly rate, 20%. So that means R sub C is 0.2. If a colony of these bacteria contains 1,000 at 8 a.m. on a certain day, find a model that gives the population of the colony as a function of time. Well, since we know that this is going to be a continuous growth model, my model form is going to look like this. Okay? And I know that my initial value is 1,000. I know that my growth rate, my continuous growth rate is 0.2. And there we go, easy enough. That is my continuous growth model. Okay, let's use the model. How many bacteria will there be at 5 p.m.? Well, we started at 8 p.m. Actually, let's type this in for y1 equals. So that's 1,000 times second e to the 0.2x. All right, that's my model. And then I just want to evaluate that model. So 5 p.m. if we started at 8, that's going to be 9 hours. So after 9 hours, we have 6,049. Rounding to the nearest bacteria, that'd be 6,050 bacteria. Okay. From the initial measurement, how long will it take for the colony to reach a population of 1 million? And what time will it be when this happens? So this is going to be a calc-intersect problem. 1 million is an output. So I'm going to go to Y2. And in this case, the unit is actually just ones. So I'm actually going to have to write out a full million. So that's, what is that? That's 6 zeros. Make sure I got that right. 1, 2, 3, 4, 5, 6. I think that's right. And then we want to do calc-intersect. I think in this case I am going to do, I'm going to look at the table. And I see I've got some E's here. So yet another confusing thing. This is scientific notation. This is not the same E. This means 7.2 times 10 to the 13th power, and this means 1 times 10 to the 6th power. So basically we're too far, and for some reason I'm at 125. So let me jump back a little bit. I'm going to go back to say 50 and see what my table looks like. So it's actually still too big. So let's just start at 0 and then go in jumps of 10. So that gets you there very quick. So actually I can see right here that this happens sometime between 30 and 40, because there's a huge growth between 30 and 40. So let's go to 40 and zoom fit. And now we have a nice intersection, which is 34.54 hours. Right, that's what that is, 34.54 hours. So if we started at 8 a.m., that's 24 would be the next day, and then we've got another 10.54 hours after 8 a.m. the next day. So what does that get you to? Okay, so 10.4 hours, 8 a.m. the next day, and plus, I'm sorry, that's 4 hours. 8 a.m. plus 10 hours would get me to 6 p.m. And then I've got 0.54 of an hour, so that's going to be about 30 minutes. So it's going to be around 6:30. Exactly, that would be 0.54 times 60, 32. So 6:32 p.m. the next day. All right. What about part C? Find R, the hourly growth rate. Well, we know that RC is 0.2, and the connection between RC and R is that R is equal to e to the RC minus 1, right? So that's just from the previous slide. Right here. So we just need to compute this. So that's second e to the 0.2. And notice you got to be careful to make sure that this is the only thing in the exponent here. And our continuous growth rate is 22.14%. Okay, which notice is just a little bit larger than our continuous growth rate. And this actually is this is the same thing as the EAY. I mean, I know this isn't about money, but it's exactly the same thing as computing the EAY. Okay, we've got another example here. The annual sales of a company's flagship product were 2.74 million in 2017. The company projects that sales will increase by a continuous rate of 4.6% annually over the next few years. Write a model for the sales of this product as a function of time. So this isn't a financial model, really. I mean, I know it's about money, but this is not actually a financial model because we don't have a continuously compounded account, but we just have continuous growth. It's sort of an academic difference, but anyway. So I'm still just going to use the exponential growth model for continuous growth. So we start off at 2.74 mil times e to the 0.046 t. And that's our model. And our annual percent growth rate, that's converting from RC to R. So again, our formula is e to the RC minus 1. So that's e to the 0.046. Figure that out and then subtract 1 from it and then multiply it by 100 to get the percent. That'll give us the answer for part B. And then for part C, according to the model, what will be the product sales in 2020? We're just going to evaluate the model here. 2020 is 3 years after, so we would just be evaluating Y1 at 3. So this is a pretty straightforward set of questions, really. Here's our answers. I think you should probably do this on your own, but just to show you what I was talking about there. There's our model. Here is our growth rate computation. And then we just evaluate the model after 3 years. All right, so give that one a shot.